Okay, so last time we showed that halting problem is uncomputable. That is, there is no Turing machine that can solve it on all instances. And this technique is called diagonalization, proof by diagonalization. And there are many other results in fundamental results in math, like Cantor's proof of the uncountability of reals, Russell's paradox, that certain sets don't exist, and Gödel's incompleteness theorem, that there may not be proofs of true statements. There may be unprovable statements. So then we started this concept, which will be a key concept in complexity theory in this course, which is called reduction. So basically, you can reduce the halt problem. If you can reduce halt problem to your problem f, right, then that makes your problem f also uncomputable. That's the idea. So, and what does reduction formally means? It means that if you want to compute f on x, then there is, if there is a computable function f prime that transforms x, and then if you want to solve in fact halting problem on a program on an input x, then f prime will transform it and feed this as input to f, and the answers will be the same. Okay, so f of f prime x is the same as halt of x. When this happens, then clearly, like you have seen in subroutines or functions in C programming, f and f prime together when called will solve also halt, right. So this reduction means that halt has reduced to f, and hence f is also uncomputable. That's the conclusion. Now we will move to bounded resource. Okay, instead of this time being finite but extremely large, for which you will run the Turing machine, now we will restrict the time and the space, and that will give us complexity classes. First, it will give us P, which is the notion of practical notion of fast algorithms, efficient algorithms, and NP. So we'll only study computable functions. So for Turing machine M, we denote the maximum number of steps on an input of size n. As this. So why maximum? Well, maximum because you want to go over all the strings of length n. So all the strings in 0, 1 to the n, no matter which string is given, the Turing machine will not run more than time of n. Okay, this is the time complexity, but to be now it is more formal, it is in terms of the input length. Okay, so we don't have to worry about time complexity being different for different strings. So now we are just taking an upper bound over all the strings of length n. Obviously, it's a function of n. So as n increases, usually time will also increase. So what is that function? We are interested in that, right? And that is why we had defined asymptotics. So now we can understand this function time of n in terms of asymptotics of n. So for function t of n, let's say think of Tn as n square, right, or think of Tn as 2 to the n. So for a given function t of n, collect all the problems solvable in that much time. In fact, let me just say approximately t of n. So we are interested in those problems that are solvable in around t of n time. In a class, and that class is d time, we call it d time of Tn. D time stands for deterministic time complexity, but it basically means that there is a Turing machine which can solve a language contained in this set in time around t of n. So formally it is the collection of L's languages such that Turing machine M, there exists a Turing machine M that decides L with time complexity big O of Tn. Okay, so this is what I meant around t of n time. It's actually big O of t of n time. So all the languages for which there is a Turing machine M solving in this much time is collected in d time t of n. Okay, that's the first complexity class you learn. So for example, d time n square will mean problems solvable in quadratic time. So example, d time n are the problems solvable in linear time, right, which is extremely fast. This is like just few scans of the input and you get the answer. And there are many such problems. If you have done data structures algorithms course, you could recall that there are many interesting problems. For example, breadth first search, connectivity, and so on in graph theory, which are actually solvable in linear time. So this is d time n is the collection of those problems. So as mentioned before, we consider polytime fast. Right. So if your Turing machine runs in time polynomial in n, then we consider it a fast Turing machine. This is in contrast to exponential time. Okay, so polynomial time versus exponential time is fast versus very slow, and this inspires the definition of the complexity class P. So polytime solvable problems are the form the class P, which is union of d time n to the c. C positive reals, right. So, n square or n to the 10.5 or even n to the 100 and so on, these are all considered time complexities which are fast. All of them are included in this class P. So, P is called the deterministic polynomial time class. Let me give the full form. Okay, so P stands for deterministic polynomial time. It's a complexity class. It contains those languages, hence those decision problems, which are solvable in time n to the c for some constant c on a Turing machine. Okay, that's the full definition of efficient algorithms and efficient problems. Now, one point which has to be made here is for practical people, this may not be fast enough, especially if C is large. So, in practice, when you actually implement these algorithms, in practice, polytime example n to the 10 may not be fast. Right, an algorithm which runs in n to the 10 time is actually pretty slow in practice when you actually implement on a computer. So, this fast or efficient is always a subjective thing. In theory, we continue to call it fast or efficient because, as I already said, we are comparing with exponential time. Okay, but in practice, you have to really optimize things. So, theoretical algorithms which are polynomial time will still need work when you do the implementation. So, even worse, what can happen sometimes is n to the log n may be faster than n to the 10, okay, in practice. So, on inputs of size 2 raised to 10, right, that's the. So, I mean, what we say in theory fast, it may not be practically fast, and what we in theory say slow, it may not be practically slow, right. So, n to the 10 may not be fast, n to the log n may be faster because the input sizes are generally limited, right. So, on those inputs maybe there are theoretically bad algorithms which work practically well. So, you always, I mean, this efficiency and speed or fast and slow, when we use these terms, it's always subjective, but in the course will always mean polynomial time. Okay, that's the definition. So, we continue to use this definition because historically it has served us well. So, historically P has served as a good abstraction of fast computation. Okay, just like Turing machines abstract computers, so remove the architecture and other issues, implementation or hardware issues. Similarly, P abstracts fast computation and removes the actual time in seconds and the implementation details and the optimized algorithms. Okay, all those things get abstracted out in P nicely, and then we can study it mathematically. So historically, it has served us well. So we'll continue with this, and basically there are many interesting examples in P. So what are the problems in P? So there are many interesting examples. Okay, lots of I mean almost all the practical problems, they fall in P. So whatever computers are doing, it's generally these are P algorithms in P. If you abstracted it as a Turing machine, it's in P. So okay, enough of P. These are I must have mentioned initially. So like graph reachability, arithmetic operations, linear algebra, right, search. So all these things that you do in practice, they are all actually polynomial time algorithms. So what are the hard problems? Problems which are not even in P. Even if you give n to the 10, n to the 100 time, you cannot solve them. What are those problems? So let's now discuss them a bit. Some practically hard problems. So the first is traveling salesperson problem. Also called TSP. So this is a practical problem, and it's supposed to be hard. There are no polynomial time algorithms known since the last 5 decades. So the problem is as follows. Let G be a graph on n vertices. With edges labeled with distances. Okay, so it's an edge labeled graph and vertices. Now question is there a closed tour visiting all the nodes exactly once? Of length at most k. Okay, so this is an optimization problem, that you are given a graph which is basically, you can think of cities or you can, in a city you can think of localities and or houses, and so these are the nodes, and between houses there are these edges which are the streets, they have distances written on them. Now the salesperson or the post person wants to go to all these houses in his or her set of houses at exactly once, right? There is no point again visiting the same house. So, exactly once, and it should be a close tour. So, it start from one point, visit all the houses and come back. In obviously, needless to say, in minimal distance traveled. So, we are abstracting it in terms of length k. So, given k, the traveling salesperson, the salesperson wants to find a close tour of this much length. If it does not exist, then the salesperson can increase k and again call this subroutine. So, it is an optimization question, right? Finding the minimal close tour. What is that? Now, brute force algorithm is just go over all subsets of edges, right? But edges are at least n, and then if you go over all the subsets, it will be 2 raised to n. So, it will be a very bad algorithm, and that is the best essentially the best algorithm which is known. Okay, so, there are no good algorithms discovered yet. Second is subset sum. So, as the name suggests, you are given a set of n integers and natural numbers, and you are given t, another natural number. So, you are given n plus 1 numbers, and the question is whether there is a subset of S summing up to t. So, does there exist subset of S summing to t? Okay, that is the question. Like before, again the brute force algorithm is go over all the subsets, which is 2 raised to n, and check whether the sum is indeed t. Okay, nothing better than that is known. Notice that you can sort the numbers, but that does not help much, because still t may pick small numbers, big numbers, middle numbers, and sum up to t, right. So, sorting does not seem to help, and then you do not know what else you can do with numbers. Third is integer programming. So, what is programming? Well, programming word comes from linear programming, if you have seen that concept before. So, linear programming is the problem of solving linear system where there are also inequalities. Okay, equalities, inequalities both are there, and such a linear system you are given, you want to find a feasible point, a solution. So, that is a famous problem again in optimization, but there they want to find a real feasible point, real valued. In integer programming, you have to find an integral solution, and that seems to change everything. Okay, linear programming can be solved efficiently, there are famous algorithms known. Integer programming is still no algorithm known except brute force. So, given m linear inequalities, in m variables. Is there a Boolean? In fact, you can even ask about a Boolean feasible point. Does there exist a Boolean feasible point? So, since I'm only asking for Boolean feasible point, there are n variables, so you can fix 0, 1, that's 2 raised to n possibilities, and see whether this point is feasible. So that's the brute force, and nothing better is known. So these brute force algorithms you can check as an exercise. So 1, 2, 3 are solved. Are easily solved in time. First one, traveling salesperson, it's it's a bit harder than I said. It's not just subsets, but also the order will matter. Which house you visit first, which second, and so on. So it's actually a matter of permutations. So that gives you n factorial time complexity. You can think of it as just going over the permutations of the vertices, right? The houses. Whether you visit the first, which is the first house, which is the second house, third house, so on. So you can look at all the permutations, and if there is a close to or one of these will work. So that's a search in the n factorial space. Second is 2 raised to n, it's about subsets, and third is again 2 raised to n time respectively. Right, so work out these brute force algorithms. But these are all very, very slow algorithms. These are exponential time algorithms because if you take n to be 100, right, just 100 houses, it's not realistic in practice. I mean, the number of houses will be far more than 100. But even with 100, this is giving you 100 factorial. So it's impossible to solve. This algorithm will never stop. Right? It's an exponential search space, and that's always a problem. You don't want to get stuck in an exponential search space. So yeah, this inspires, or these problems these are all practical problems from real life, and they are exponential time. We don't know how to solve them. So these problems inspire the exponential time class. So EXP we call it. This is the d time, so time complexity 2 raised to n raised to c. Okay, so instead of n to the c, now you are talking about 2 raised to n raised to c, and that's exponential time. So these problems, the problems 1, 2, 3, they are all in EXP, and we don't know any better. Okay, so those brute force algorithms are the best we know. So notice that n factorial is smaller than 2 raised to n square. So clearly d time n factorial is contained in exp, and similarly d time 2 raised to n is also contained in subset of exp. So these problems are clearly in exp, but we don't know anything better, and we would like to know better because these are all very useful problems. These are not artificial problems. They all have connections to combinatorial optimization. So these problems have one thing in common, that if somebody gives you a solution, you can verify it, right? So if somebody gives you a closed tour, salesperson can verify whether this closed tour satisfies the properties and length is less than or equal to k. If somebody gives you a subset, you can test whether the subset sums to T. And if somebody gives you a Boolean feasible point, you can check whether it's feasible, right? Very efficiently. It's trivial to do those verifications. So these verifications protocol are it seems trivial, but actually it's an interesting feature of these problems. And we'll collect those problems in exp which have this feature and give it a name. So they have a common feature given a closed tour, a subset or a Boolean point, it can be verified. Whether it's the right one. Whether it's, let's say, correct in a short time or by an easy algorithm, let me say. So this brings us to the concept of polytime verifiers, polytime verification. So this motivated Cook and Levin to study all the problems that have polytime verifiers. Okay, so these problems we collect in a special complexity class which we call NP. So language L, obviously Boolean language decision problem, is in NP if there exists a constant and a polytime let me say now Turing machine such that for all x, for all input x, x is in L if and only if. So, basically yes strings of your decision problem L, if and only if there is a certificate U which is not too large okay, this is where C is being used. The certificate U could be bigger, slightly bigger than the input length, but not too much, only up to a polynomial blow up, and then M can certify it, verify it. Okay, so M here is the verifier checking whether given U is correct solution or not.